Okay, guys, this video is going over 1-6. So it's not covering everything in 1-6, but 1-6 is our last visible learning objective in Unit 1. So our Unit 1 test is getting close. What I want to focus on in Unit 6 is kind of just define some different things. So 1-6 is about the structure of different types of solids. So we're going to define the different types of solids that we're going to be responsible for kind of having a general idea of what their structure is and how strong their structures are in terms of like melting points and stuff. But the main thing for this lesson is just kind of getting used to the way the College Board AP will depict the types of solids and the different ways, what to look out for. Like if you see something like this, that means it's ionic. If you see something like this, that means it's a metal. If you see something like this, that means it's a network covalent solid. So just kind of the types of representations of the solid structures that you need to be familiar with. So we'll go over that. And again, it's not all of 1-6, but it'll help you get the ball rolling with 1-6. Okay, so let's look into this. All right. So the types of solid structures that you're responsible for are kind of listed here. So we have something called network covalent solids. And in particular, it's going to be these three, right? This is what you want to memorize as the network covalents. Now, I saw one question on a practice test where they mention I2 as a network covalent, and that's fine, but that wasn't the answer to the question. It was just kind of a reference. So what you need to recognize as network covalent structures are solid carbon, so graphite, diamond, solid carbon, solid silicon, notice they're in the same group, and then something called silicon dioxide. All right, that's a network covalent. All right, and as soon as you recognize one of those, most likely that's going to be the strongest structure that you're going to see. Network covalents tend to be the strongest of the structures. Now, there's always exceptions. Some metals have really strong structures and have high melting points. But if you're not given any other information and you're asked to list things in order of increasing melting point or boiling point or all that stuff, number one on the list, the highest melting point, the highest boiling point, is going to be a network covalent structure. So if you're given solid carbon, that's going to be number one on your list. Solid silicon is going to be number one on your list. Solid silicon dioxide, number one on your list. Okay. Next, we're going to talk about ionic solids. So ionic compounds, salts. A lot of times the structure is referred to as a lattice structure or a crystal lattice, and that's for ionic compounds. Then we're going to have metals, and the main thing to focus on metals is truly understanding the definition of what a metallic bond is. And then as we talk about different types of metal structures, we're going to get into alloys. And alloys are just mixtures of different metals, different solids mixing together, not chemically combined, but physically combined. And what you want to understand is alloys. There's two types. There's interstitial alloys, and then there's substitutional alloys. And so we want to differentiate between those. And then we have molecular solids. You can call them covalent solids, so not network covalent, but just regular covalent. So we're talking about organic compounds, like large organic compounds that could have functional groups, so they could be polar, or they could be just very large carbon chains that are nonpolar, but they have very high London dispersion forces, so they're still solids, like plastics and things like that. Really it's just, how is nonpolar depicted versus polar, that kind of thing. All right. So let's talk about network solids. So again, you want to memorize anytime you have solid carbon, solid silicon, or silicon dioxide, that's a network structure. Now, they don't usually represent, they're not going to really tell you, what does this represent, and you need to know it's a network covalent, but these are how network covalent structures are usually represented. So like carbon is in a tetrahedral structure, so a bunch of carbon atoms tetrahedrally bonded to each other, right, in 3 dimensions, right? And notice like silicon dioxide is a little bit similar. Here's an alloy of silicon and carbon, silicon carbonide. So all of these would be networks. So what network means is just, this carbon is bonded to 4 carbons, and those carbons are bonded to 4 more carbons, right? So each atom has a network, right? And it's spread. It's like, I know 2 people, then those two people tell 2 people, and then they tell 2 more people, and it's kind of like an exponential thing, right? The reason why diamond's so hard is if I push on this carbon right here, I'm really pushing against all the carbons in the structure. And so I push on that carbon here, all the carbons in the structure push back. That's why diamond's so hard. Now here's graphite. So notice they're kind of in a 2-dimensional network, and then each layer is only bonded to each other in terms of London dispersion forces. So there is no covalent bond between this layer of carbon atoms and this layer of carbon atoms. And that's why graphite is good for pencils, because what you're actually doing when you write on your pencil is because the layers of the graphite are only connected via London dispersion forces, just simply pressing down on the graphite leaves, sheds off layer after layer after layer of carbon. But regardless, graphite has a very high melting point. It's a very strong structure, diamond as well. And then the other network covalents are silicon dioxide and silicon carbonide. So that's what to look out for. So the main thing is maybe you won't have to, you probably won't be given a representation of a network covalent like this, and you have to identify it as such, but you just have to recognize that these things are network covalents, and they're going to be the strongest of your structures, okay? Now let's go to ionic. So there's a lot to know about ionic, and one of the main things you want to know is ionics, if you know you have an ionic solid, it's not going to conduct electricity in the solid state, okay? But ionic compounds can conduct electricity. They are good conductors of electricity when the ions can move. So there's 2 times where the ions can move. When they're dissolved in water, okay, because when the ions are dissolved in water, the ions pull apart and they're separated from each other and they're mixed with the water molecules. And the cation is surrounded by the oxygen side of water molecules, and the anion is surrounded by the hydrogen side of the water molecules. And now the ions can move. So when they're aqueous, they can move, they can conduct electricity. So salt water solutions conduct electricity because they have moving ions, okay? And then the other time is when they're melted. But because ionic structures are kind of the second strongest structure on average, other than network covalent. So it normally goes network covalent is the strongest, then ionic structures are the next strongest. You have to get them to a very high temperature to be melted. And that's why a lot of times they're referred to as molten. But when they are in the liquid state, the ions can move. So liquid ionic compound can conduct electricity, just not the solid, okay? Now there's a lot of ways these are going to be represented, okay? A lot of times you'll know they're charged because they'll put a minus sign in one of the spheres and a positive sign in the other sphere, okay? So here's kind of an example of the way an ionic compound is structured. So a negative ion, a positive ion, a negative ion, a positive ion, a negative ion, a positive ion. And notice that you don't get any negatives right next to negatives, and you don't get any positive right next to positives, and that should make sense to you, right? So if I saw something like this, I would know that that would be a representation of an ionic solid, okay? So I know this right now, in the state it is in right now, won't conduct electricity, but if I could get these ions to move, so if I could melt it and make them move out of their fixed position, or if I could put them in water and now they can move around with the water molecules, then it would conduct electricity, but right now it would not, okay? So here is another representation. Now, if this were on the AP exam, you would have to be told that this was an ionic compound to know that each sphere represents, a cation and an anion, okay? But this could also represent an alloy if these weren't ions, okay? So if you see that, they're telling you they're ions, right? Here's a positive ion, here's a negative ion. So I know that's an ionic solid. Seeing this, I'd have to be given more information to know whether this is an alloy or whether this is an ionic compound. All right. But let's say you were told it was lithium fluoride. Now, here's where you have to know the radius trend, and in this case, ionic radius trend. If this were lithium fluoride, you'd have to be able to know that the green ones are the fluoride and the purple ones or the blue ones, whatever color you want to call that, are the lithium ions, because you should know that lithium plus 1 is smaller than fluoride minus. And the way you would have to know that is you'd go to your periodic table and you know that lithium 1 plus is smaller than helium, and you know that fluoride F minus is bigger than neon, and you know helium is smaller than neon. So if you were told which ionic compound this was, and lithium fluoride in this case, you'd have to recognize that the smaller sphere is the lithium ion and the larger sphere is the fluoride ion, okay? If you were told this was cesium fluoride instead, then it would be flipped, and you would have to know that the smaller ion is fluoride and the larger ion would be the cesium 1 plus ion. All right, so knowing, if I know that this is an ionic lattice, you'd have to know, okay, well, which ion is the smaller one and which ion is the bigger one. And so, you'd have to know which ions are which to get that. So make sure you understand that about it. All right. So again, if I saw this, I would know this is ionic because I got a minus and a plus and a minus and a plus and a minus and a plus. I don't have two pluses right next to each other. I don't have two minuses right next to each other. All right. Now, another question that comes up every once in a blue moon on the AP exam is something called a cleavage point, and it's for ionic compounds. And that's when you force the structure into a positive next to a positive and a negative next to a negative. And so when that happens, right, the ionic compound breaks apart due to Coulombic repulsion. So it's a reason why ionic compounds are kind of brittle, right? If you moved them around in your hand, they'd start to kind of fall apart. And that's because, if you add pressure, you could force like ions next to each other. And as soon as like ions get next to each other, they, fall apart. Okay. So when they ask, what's a cleavage point or the cleavage of an ionic solid, you'd be looking for something like this. So this is the normal structure when everything's all happy and the positives are next to the negatives and the negatives are next to the positives. But all of a sudden, if I forced a positive next to a positive and a negative next to a negative, boom, cleavage. Okay. So here's an example question. This is from an old AP exam. Which of the following diagrams best illustrates how a displacement of an ionic crystal results in cleavage? All right, so first off, let's do process of elimination. We're going to learn that this diagram right here represents a metal, because what it is a bunch of positive nuclei next to each other with electrons kind of free flowing in between, and that's a metallic structure. This is a hydrocarbon, obviously, so you got carbon, 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 and each carbon has either three hydrogens on it or two hydrogens if they're one of the middle carbons. So this is just a big hydrocarbon. So these two are representing ionic structures, right? Negative, positive, right? But this one's showing before the cleavage, after the cleavage. So before the cleavage, we got our normal ionic structure. And then the cleavage is when the minus is next to the minus and the plus is next to the plus. Okay, so just kind of showing you an example of when these structures are going to be shown on the AP exam. All right, so just another example, the intact crystal and then the cleaved crystal. All right. So for metal structures, again, it's important to understand the definition of a metallic bond. We say metallic bond is a sea of valence electrons, mobile electrons, what we like to call, in AP, we like to say delocalized electrons. So there are electrons that are not fixed to a nucleus. So notice that this is a little bit different than how we would represent, an ionic compound, right? This has positives and negatives, but notice the negatives are a lot smaller and they're not in the same position throughout the structure. They're kind of in random positions throughout the structure. So what this is supposed to represent is the positively charged nuclei of the metallic atoms, okay? So, copper nucleus, copper nucleus, copper nucleus, copper nucleus, copper nucleus, copper nucleus. So repeating positive signs, and then you have really small negative signs, and those are supposed to represent the electrons. And what you're going to notice is they're kind of in random places, right? So they are free to move from one nucleus to another nucleus. And that's why it's important to understand that if you have a metallic structure with what we call metallic bonding, which means the electrons they're not local to one nucleus. This electron isn't stuck here around this nucleus. It can go down the line and flow throughout the structure. Metals will conduct electricity to solids. That doesn't happen in an ionic structure. In a solid ionic structure, you can't conduct electricity. But since metals allow for the motion of electrons from nucleus to nucleus to nucleus to nucleus, they conduct electricity as a solid, all right? So here's kind of another representation. Notice I don't have like positive, negative, positive. It's just a bunch of positives next to each other, and then we got these really small electrons. And notice they're not in a fixed state. They're kind of randomly allocated, showing you kind of the random motion of those electrons. So again, here's another representation of the of a metal structure. All right. Here's another one. Notice that the negative charge isn't its own sphere. It's just kind of negative charge. So you have the metal nuclei next to each other, and then the electron cloud free to flow between the nuclei. All right. All right. So within metals, we want to talk about alloys. So an example of an alloy is steel, which is a mixture of iron and carbon, or brass, which is a mixture of zinc and copper. So in these structures, we're not going to see identical spheres to represent the nuclei, because we're going to have different nuclei. So we're going to have, zinc atoms and copper atoms, or iron atoms and carbon atoms. And the important thing that you need to differentiate in AP chemistry is if the alloy is substitutional or interstitial. So let me show you. This is a substitutional alloy, and this would be interstitial. And the difference is the radius, right? When you have similar sized atoms, then you're going to get a substitutional alloy. So like let's say the darker ones here are copper and the red ones are zinc. So in order to get zinc in this structure, I'd have to take out a copper atom and put in a zinc. It substitutes. It's substitutional. Okay. Interstitial is when you have one big, you have a big radius atom and you have a small radius atom, and the smaller radius can fit in between, right, in that hole kind of in between the spheres of the larger atoms. So this, if this were steel, the bigger atoms here would be the iron, and then the smaller ones, the red ones here that are filling in the holes, are going to be the carbon, right? So, you might have high carbon steel where a lot of these holes are filled in with carbon, or you could have low carbon steel where you only have a few of the holes filled in with carbon. That's the real difference. But the main thing is to understand, well, I know that iron is much bigger than carbon. So if iron and carbon make an alloy, it's going to look something like this. It's going to be substitutional. But I know that copper and zinc are similar sized. So when they make an alloy, it's going to look like this. It's going to be substitutional. And, it just depends on how much of each thing that you use to mix. Like, do you have more zinc or less zinc? Do you have more carbon or less carbon? That kind of thing. All right. All right. So here's an example. Which of the following diagrams best depicts an alloy of nickel and boron? This was actually on the AP exam a couple years ago. Well, let's say an alloy is not ionic. So we know it's not this one right here. That's an ionic structure. So we can cancel out that choice. This would be kind of how they would show a molecular polar solid, right? We know it's covalent, right? Because you don't have fully separate spheres. You have this atom connected to that atom. So that would represent kind of a covalent bond. So this would be kind of maybe a depiction of a polar covalent solid. All right, so these choices aren't going to be it. So it's really, would we expect nickel and boron to make a interstitial alloy or a substitutional? Well, if you look at your periodic table, boron, is a lot further up and to the right on the periodic table. So I know that boron's going to have a much smaller nucleus than nickel. So nickel and boron would make an interstitial alloy, right? Maybe if this were nickel and, another transition metal, nickel and iron or something, then it would be, substitutional. But because it's nickel and boron, and that boron is a lot smaller than nickel, this is what we would be going with. All right. All right. So molecular solids, it's not really going to be about being able to depict the diagram, but here's kind of like, solid water. So which would be a molecular solid. So you got the water molecules, and then you got the hydrogen bond interactions and stuff like that. But again, here would be an example of how they might try to represent a molecular solid. And if we go back to that other question, here would be a hydrocarbon solid, right? That's how they would represent it. What we need to know about molecular solids versus, like, let's say ionic solids and metallic solids is molecular solids, covalent solids, don't conduct electricity in the solid state, and they don't conduct electricity if they dissolve them in water. So that's really what you need to know. So we're going to finish up this unit with a lab where I give you two ionic compounds and a molecular covalent compound. And you have to determine which one's which. So, the first test would be, and let's also throw in a metal solid in the mix. So how could you test which one's the metal? Well, see if they conduct electricity as solids. If it conducts electricity in the solid state, then it's a metal, all right? If it doesn't conduct electricity in the solid state, it's either going to be a molecular solid or an ionic solid. So that's what you would be thinking. And then what you would say is, okay, well, let me dissolve them in water, right? Sugar dissolves in water, that's a molecular solid. Salt dissolves in water, that's an ionic solid. But salt water will conduct electricity because salt water has moving ions in it, whereas sugar water does not conduct electricity in solution. So the sugar water wouldn't conduct electricity, and the ionic solid would conduct electricity. So that's kind of what you need to know about molecular solids. If they're polar, they would be water soluble. So if we're talking about a big organic compound and it's just a hydrocarbon, then that would be non-polar. It wouldn't dissolve in water. But if we're talking about sugar, which has functional groups and stuff, or an alcohol or something like that, that would dissolve in water, but the resulting solution would not conduct electricity because the resulting solution wouldn't have ions flowing in it. The only time you could get ions flowing in is if you dissolved a salt or an acid, but we're not going to really talk about that too much right now. All right. So that kind of goes through, the kind of diagrams you're going to be responsible for in 1-6. And so really what it's going to come down to is putting 1-6 and 1-5 together, where I give you a list of different elements and compounds, and based on their classification, are they network covalents? Are they ionic? Are they metals? Are they just covalent, molecular? Being able to rank them in terms of, highest melting point, strongest structure, highest boiling point, that kind of thing. And so what we're going to make sure we understand is, if one of my things is a network solid, that's going to be on the top of the list. That's going to be the strongest structure, right? Next are going to come my ionic compounds, and then after that, any metals, and then after that, molecular, covalent, okay? And then, the ionics, you separate based on Coulomb's law, so the smaller ions, the stronger the structure, and the higher the charge of the ions, the stronger the structure. Metals, it's basically the most dense metal, so the smallest radius metals are going to be probably the stronger structures than the larger radius. Usually it's the transition metals that are the strongest, and like the metals furthest to the left, so the alkali metals, the alkali earth metals, they're not as strong to structures, they have lower melting points. And then it's going to come all the covalent stuff. And then when you get to the covalent stuff, then it's just your normal IMF stuff. So am I polar with hydrogen bonding, or am I polar just with dipole-dipole? And then if I'm nonpolar, how strong are my London dispersion forces? If I'm nonpolar with more electrons, I get greater London dispersion. Nonpolar with less electrons, I have weaker London dispersion. And so that's what it's going to boil down to. So that's kind of it for 1-6, or the intro. We'll do some practice and stuff in class, and we're wrapping it up. So almost done with our first unit, and we'll be moving on to Unit 2 before you know it. All right, so have a great one.